Okay, welcome back to our first video notes in quite some time, actually. We took a little bit of break so that we could get some things corrected and do a couple other things. We're coming back now to kind of wrap up our unit, or our first half of the electricity unit, which is on mostly electrostatics, and we're going to be pivoting towards circuitry. And this topic, electric potential, kind of bridges the gap between those two. To start off, let's review what an electric field is. Remember, a field, any type of field in physics, is a change in the space around something. And in this case, an electric field is a change in the space around an electric charge. A change in the space around an electric charge. As in, the electric charge, it has this property where it alters the space around it, and that causes other charged particles near it. Well, it has some effects on those particles without ever touching the charge creating the field itself. All electric charges create fields. Other charges then interact with the fields created by those charges. So, we measured electric field strengths. And one of the things that was a little confusing is, what does the strength of an electric field tell you? And I said, think about the units. Well, the units are newtons per coulomb. Okay, so newtons per coulomb. So what this tells us, it's kind of like, I think I made the analogy, it's like a unit price. Okay, you go to the grocery store, you want to buy a 24-pack of soda, and it costs, I don't know, let's say $12. That means that each soda, the unit price is let's see, the unit price would be 50 cents per soda, okay? Electric field is kind of like that. How many newtons of force acts per coulomb of charge interacting with the field? So how many, let's see here, how many newtons of force act per coulomb of charge? And this is the charge that is, I put in quotes, interacting or experiencing with the field. Remember, with electric field, there was this kind of tricky thing where you had to think about, is this the charge that is creating the field, or is this the charge that's simply reacting or interacting with the field? So what an electric field strength really tells you is, based on how much charge is interacting or in the field, how many newtons of force are going to get put on it. So, for example, we have a set of parallel plates over here. They're oppositely charged. Let's say they create an electric field of 100 newtons per coulomb between them. The electric field, and first let's draw the field. It's parallel plates, so we know that we're going to have evenly spaced electric field lines, because that indicates that the field is the same at all locations. Okay. The electric field intensity, or strength, 100 newtons per coulomb, what that tells us is that for each coulomb of charge in the field, so that means in here, not the plates themselves, but the plates create the field, we're talking about the space in here. For each coulomb charge in the field, 100 newtons of force acts on the charge. So what that means is, if you have 1 coulomb of charge in here, that leads to a force of 100 newtons on that coulomb. If you have 2 coulombs of charge, that leads to a force of 200 newtons. So see how an electric field strength helps you to find out how much force is going to be put on a certain charge. If you had, let's say, 8.5 coulombs, let's see, if there's 100 newtons per charge, or per coulomb, that means there would be 850 newtons acting on that charge, okay? It's very simple. So, if we do put the positive 1 coulomb charge in between the plates, what's going to happen? So if we put a little 1 coulomb charge up here, then it's going to experience, as we said, a 100 newton force. And which way will it be directed? If we put a positive charge up here, it's going to be repelled away from this positive plate and attracted towards this negative plate, right? So it's going to experience a force downward. The electrostatic force is going to act on this charge. It's going to push it downward away from the positives toward the negatives. So the 100 Newton force is directed toward the negative plate. And if the force is directed that way, let's assume that there's no other, forces acting on this, then that means that, well, that's the net force then, and so the object will accelerate that way. The charge, therefore, accelerates that way. And here's where I'm going to start bringing in something new. When we talk about electric fields, they kind of line up with forces nicely, because what a field does is it tells you the size of the force based on how much charge is in the field. Well, let's look at it from another perspective. If we know that the charge is accelerating, that means it's speeding up. Its velocity is increasing as it goes down. And if the velocity is increasing, then we know that, let's say, the kinetic energy is changing, isn't it? And why would the kinetic energy be changing? Because work is being done. And let's go back. What is work? How does work get done in an object? A force moves something over a distance, and that's exactly what we have here. A force, an electrostatic force, is getting put on our charge as it moves over some displacement. I should be saying displacement. So you know from previous topics that when a force is applied to displace an object, that means that work is done and there's some sort of change or transfer in energy. In this case, it happens to be, well, the object's gaining kinetic energy. Well, the question is, where did that kinetic energy come from? The answer, and it's not, this particular part isn't as important as to what it leads us to. If we were to put the 1 Coulomb charge up here, when it's placed near the positive plate, it acquires what is called electric potential energy. And when it's released, let me do this. When you put it up here, the 1 Coulomb, positive 1 Coulomb particle, we put it up here. This is where the object or the charge has very high, I'm just going to abbreviate it, EPE. There is a formula for electric potential energy, but it is not important that you know it. We're going to get to something else that is more important. What happens is this particle will start to move, right? It'll be repelled away from the positive charges towards the negative charges. So after its release, as it gets farther away from those positive charges, it starts to lose that electric potential energy. What does it turn into? Well, now the particle is moving, so it starts turning into kinetic energy. And then by the time it gets all the way down to the bottom, the negative plate, or just about to the negative plate, just barely above it, down here, all electric potential energy has been turned into kinetic energy. And again, how did this energy transfer or change happen? Well, you had work done by the electrostatic force to turn electric potential energy into kinetic energy. So, the force that is on this particle acts over a certain displacement. That means work is done, which means energy is transferred or changed. It gets changed from electric potential energy when the positive charge is near the other positive plate, to kinetic energy as it repels away from that, gains speed, and goes towards the negative plate. So, like I said, electric potential energy by itself isn't all that important, because if you can imagine, if I were to maybe cut this in half, if I were to cut this charge in half, it wouldn't have as much electric potential energy. Okay, if I reduce the amount of charge, well, it wouldn't be as affected, and possibly that changes what happens as it moves down. Okay, because it doesn't have as much electric potential energy, it probably can't get losing my words here. Because it doesn't have as much electric potential energy, not as much kinetic energy can be generated as it gets transferred. So what we want to do is we want to come up with a way to kind of simplify this. We don't talk about electric potential energy that much. What we're going to talk about instead, because electric potential energy depends on what you put in here, we'd like to talk about the rate, and it's not really a rate, that's kind of a rate, the rate of energy transfer per amount of charge. Just like we talked about electric field up here, and that was the newtons per charge, the amount of force per charge in an object, we want to talk about, for this set of parallel plates, not just how much energy is transferred, but the energy transfer per charge, the energy change per charge. And that's where we come and talk about electric potential difference, okay? Now this is a very wordy term. I want to point out that this word potential is a noun. You guys usually use potential to mean a verb or an adjective of some sort, describing something. Potential here actually is a noun, okay? It's a thing that can be measured. Electric potential, so that's a thing, difference, the difference between electric potentials. The definition of this is the change in energy or work done per unit of charge between 2 points in an E field. An E field obviously is just an electric field. The change in energy between 2 points the change in energy per unit of charge between 2 points in an E field. Again, like I said, if we put more or less charge in here, the energy change would be different. What we want to know is, because of this electric field, what is the difference between, let's say, here and here in energy per amount of charge that's put in, okay? But if we know, so essentially, if we know how much charge is put in, we can make a calculation about how much the energy changed. This actually has a lot of names, this idea of electric potential difference. It's also informally called voltage. And you'll hear many, many, many different terms for this, because there's even more than that. I will call it at different points electric potential difference. I will call it electric potential. I will call it potential difference. I will call it voltage. I'll call it voltage difference. The key is we are trying to find the difference in energy per unit of charge between two different points in an electric field. Because an electric field gets set up by other charges between any 2 points in that electric field, what is the difference between what is the difference in energy per amount of charge between 2 points in an electric field? Some other real quick notes about this, and then we'll next video we'll get to some examples. Positive charges. When you put a positive charge in an electric field, it will move from high potential, and high potential means it's near other positive charges, to low potential, which can mean two different things. Either it means far away from positives or near other negative or near negative charges. Okay? You're probably thinking that we need some sort of symbol for this. I'm going to go to the electricity page. And so far we have looked at the first two equations, Fe equals KQ1 Q2 over R squared, E equals Fe over Q. We're now down to this equation, V equals W over Q. V being potential difference, there's one of those alternate names.